Hello guys, welcome back to Maison African Motives. Still working on electrical trade theory N2. In this case, we are going to be focusing with a full paper from the question paper which was written in July 2022 X paper. All right, so this is what we have, guys. Our paper is 6 pages and so forth. So we shall quickly rush through the paper and see what you're given. Remember your instructions, mostly that you are supposed to have correctly your answers written. The sketches must be neat, labeled, and large enough to show the required detail, and answers must be given correct to 3 decimal places. This part here to 3 decimal places. Marks will not be allocated for incorrect SI units. So take note, when you are dealing with the units, you are supposed to apply the actual unit that is needed. If wrong units, then you are not going to have a mark for that. Okay, so here we've got questions. First part of question number 1 on alternating current circuit theory, where we are given to define the following terms. Define the following terms. The first part is instantaneous value. What is the instantaneous value? And that is 2 marks for that. Okay, the instantaneous value can be defined as smaller values occurring at a specific instance. So these are smaller values that are occurring at specific instance before or after the maximum value of a wave. Like if we are given a sine wave like this, okay, this is our maximum, this is our minimum. So instantaneous, these are values which are taken in between from the maximum or before the maximum, any value that is taken at a certain point or at a certain time that is given. All right, so that is what was the part of this question. All right, we move on to the other part of the question, which is on 1.12 to define or to give a definition for the average value. Also having 2 marks for this. Okay, so this is what we have for the average value. We can define this as average values of all instantaneous values during one cycle of a sine wave. Or we can have this as the average value of a wave of the waveform represents the average values of all mid-ordinates taken over half a cycle of a sine wave. So this is what we can give in our explanation or in our definition of the average value. Then we've got 1.3, the power factor. So remember that our power factor from the power triangle, this is the ratio. So this can be taken as the ratio of true power to apparent power. So this is the ratio of the true power. That is the ratio of true power to the apparent power, all right, to the apparent power in this case. Remember that power factor is equivalent to P over S, which is the apparent power in this case, all right? So this can give us the power factor, which is cos theta, which is equal to cos of theta. All right, on 1.3, we are given 1.2, we are given a 3-phase delta. Okay, so this is a delta connected motor which draws 35 amps from a 400 volt supply at a power factor of 0.8 lagging. Determine the following. All right, so we have got a 3-phase. So I'm just going to take the information. It's a motor and it's a 3-phase in this case. All right, so this is 1.2. All right, so that's 1.2. So we're given it as a 3-phase motor in this case, which is in delta. All right, is this delta or is it star? All right, that's a 3-phase delta connected. Okay, so I've given if it draws the current that is drawn from the supply is the line current, and this is the line voltage. So we're given the line current of 35 amps. So we have got the line current of 35 amps and the line voltage in this case of 400 volts. And we are given the power factor lagging of 0.8. So that is our power factor, which we said power factor is equal to what? To the cosine of theta. So we are given the power factor of 0.8 lagging in this case, all right? That is lagging. So which means from the power factor, we can determine the angle theta between, because remember that cosine of theta, or let me have this way, the power factor is equivalent to the cosine of theta. So meaning to say, this power factor of 0.8 can be written as cos theta is equal to 0.8. So we can determine our theta. Remember from our mathematics, theta is equal to the arc cos of 0.8, which is shift cos on your calculator. So this is going to give us the angle of 36. So this is going to be 36,8698. If you round to 3 decimal place as per the instruction of the question paper, that's 1, 2, 3. The 8 is going to change this 9 into 10. We give a 1. So this is going to be a 7. So we are going to have 36,870 degrees as our theta, or just 36,87. All right. So this information is just important before you start attempting the questions. All right. So now we can attempt our question. The first part of the question is to determine the following, or to calculate the following. 1.21, the reactive power. So remember that reactive power taken from the line current and the line voltage can be calculated. This is Q representing the reactive power. So 1.21, we have to calculate Q, which is equal to, this is a 3-phase. So in 3-phase, it is going to be the square root of 3 times the line voltage times the line current times the sine of theta, which is measured in what? Which is measured in verse. So this is the formula that you're also given in your formula sheet under 3-phase, okay? Under the reactive power. So we can simply substitute of it, because these are line values. We are given line current, line voltage. So there's no need for you to calculate anything in phase. You are using line voltage and line current. So this is going to be the square root of 3 times the line voltage, which is 400, times the line current, which is 35, times the sine of theta, which is the theta that we calculated here. So this is going to be sine 36,87 degrees, which is just 870, is just comma. It's just same as 87 after the comma. It's just one and the same thing. All right, so make sure that you use your calculator properly in degrees. Make sure that your calculator is in degree mode. We are going to obtain 14549, 26, something like that, which is measured in bars. So we are not given, are we given, is it in kilo? We are not given, you just calculate reactive power. So we can just even leave our answer like this, or we can convert to kilovars. If we are to convert to kilo, this is going to be divide by 1000. So it's going to be 14,549. These two cannot change 9, so it is going to be 49 in kilovars. All right, so this is these are the units for reactive power. All right, from your formula sheet, Q is given, everything, you have it, so you just have to take direct from your formula sheet. Also, you're given the apparent power. So the apparent power is given by the letter S, all right, which is equal to voltage times current, but it's for 3-phase. So you multiply by square root of 3, because it's for 3-phase, all right? So we are going to use line voltage and line current again. All right, so this is what you're going to have in this case. Let us just have it here. That's 1.22. All right, so that is S is equal to voltage times current, but for 3-phase, it is going to be multiplied by square root of 3. For single phase, you do not have this square root, okay? So that's line voltage times the line current in this case, which is measured in vars, in volt amperes, not vars, but volt amperes. All right, so S is going to be square root of 3 times the line voltage, which is the same as the one that we had before. Still, we haven't changed anything, which is 400, times the line current, which is 35, times, all right, so that's it. We are not multiplying anything in this case. These are the units, all right? So that means we are going to obtain something like 248, 7113 and so forth. So you can write it to kilo volt amperes divide by 1000. This is going to be 24,24. This 7 is going to change this 8 into 9. That will be in kilovolt amperes. So that is what we have. If it is true power, it is going to be cos of theta, square root of 3 VL IL cos of theta for true power, which is measured in watts or kilowatts. But for reactive power, we use sine of theta. For apparent power, we do not have any sign. We just multiply voltage and current with square root of 3. That's it. All right, so that was the part of the question. Let's check what we are given on the other part. The phase current, in this case, the phase current. Remember, we are dealing with delta. In this case, we are in a delta and we are given the line current and we are in delta. All right, so remember, in delta, that is 1.23. Let me just write it here so that we can just take our information from this one. In delta, remember that the line current is equal to the square root of 3 times the phase current, which is also you are given this formula in your formula sheet. So we need to calculate the phase current in this case. This is the one that the question is asking you to calculate. So we can simply divide, because we need this one. So we can divide by the square root of 3 by the square root of 3 both sides. So we can remain with the phase current. So the phase current is going to be the line current over the square root of 3. So that is your line current. We have got your line current, which is 35 over the square root of 3. So this is going to give us the phase current. All right. So if you simplify properly, you're going to obtain 20,20725. So this is going to be 7. The 2 cannot change the 7. So it's going to remain as it is in amps. So that's current. Current is measured in amps. So be careful. Be very careful in terms of the units. Remember, wrong units means that everything is wrong. Yeah, they are not going to mark anything for wrong units. So the answer will be wrong. Okay, so that's what we had on this first part of the question, question number 1, on alternating current circuit theory, having a total of 12 marks. All right, so that's a lot in exam. That's a lot. We move on to question 2 on conductors, insulators, and cables. 2.1, choose an item from column B that matches a sentence in column A, write only letter A to E. So you're just going to take the letters from this column B, which matches with this description in column A. All right, so on the first part, we are given 2.11. The most commonly used, okay, let me use the blue one, this one. The most commonly used insulation, especially for conductors and cables, is the most commonly used insulation. So that's our PVC in this case, which is C. Okay, so this one is our PVC, which is C. So the answer there is C. Silicone is used to insulate conductors exposed to relatively high temperatures in which part? That is in electric stoves and heaters, which is on D. So this is D here. An insulator that does not react to chemicals. Which insulator that does not react to chemicals? That's a ceramic. It's an insulator but does not react to chemicals. So that's E. An excellent insulator for high voltage components, transformers, and other electrical machines working at extreme temperatures is known as, it's an insulator, this one working at high temperatures. So that's a silicone, which is on B. So you can have the B. And good insulator that can withstand high temperatures, which is A, that's asbestos, can actually withstand high temperatures. So that's A, which is the asbestos in this case. All right, so that's what we had. Okay, if we haven't got any vice versa in terms of marks, please, in terms of allocation of answers, please let us know so that we can rework on this part, so that we can also rework on it, or any other contribution that we have. Let us know so that we can add in our next revision. All right, we move on to the other part of the question, which is 2.2. We are now On 2.2, we are now given a 220 single phase supply is connected to a load that draws a current of 5 amps. If the total resistance of the conductors is 0.8, calculate the following. So take note, we have a supply voltage, which is this one is a single phase, so we can just save it here. So we've got V supply of 220 volts, and it's connected to a load. So the load is actually, we are taking a current across the load of 5 amps. So this is our total current in actual sense. If the total resistance of the conductors, so there are conductors in between this circuit that we have, so we can just have this as the total internal resistance of the conductors, which is 0.8 ohms. So the question is asking us to calculate the voltage drop between the supply and the load. Take note, before we are to reach, we are having something of this nature. This is what we have. This is maybe, let's just say this is our load here. All right. So we have got the input, which is our VS. Then the cables or the conductors that we have, they have a certain resistance. So this resistance is going to give us a voltage drop across, a voltage drop that is in between the supply and the resistance, which is taken from the total of any other part which is not the load. This is your load. So any other part which is not the load, which means we are talking about these other conductors. So this can help us to calculate the voltage drop. So on 2.21, we are going to have our voltage drop in this case as the total current times the total of the internal resistance, which is the resistance of the conductors. So that is total current of 5 times 0.8. So this is going to give us 4 volts in this case. All right. So that is our voltage drop, meaning to say before we are to reach the load, we have lost 4 volts across. Okay. Now the question on 2.2 is to calculate the voltage across the load now. That is from the voltage drop. Okay. So remember, we have a voltage drop from the supply that we had. We were having a supply of 220. We have lost 4 volts. So this is now the voltage that is going to be across the load. So meaning to say the voltage across the load is going to be equal to the V supply minus the voltage drop that we calculated in this case. So this is going to be our supply voltage of 220 minus a voltage drop of 4 volts. So if we are to subtract, we are going to obtain 216 volts, which is the voltage across the load now. So that is how we can attempt these typical questions. We just have to be careful on how you answer your questions and so forth. Okay, on question 2.2, we are given to state 3 disadvantages of installing cables in ducts. Okay, what are the disadvantages of installing cables? Okay, so this is what we have. We've got the disadvantages that the ducts, they are expensive. Okay, it is time consuming process to install ducts. Ducts do not always allow for effective heat dissipation. So this is going to affect us in the installation of these cable ducts. Okay, so this is what we asked and what we needed. I think with these points, they are enough. On question 3, which is on switchgear and protective devices, we are given on 3.1, switchgears are used in an electric power system to control, to protect, and to isolate electrical equipment from abnormal conditions in an electric circuit. Name 2 switch gears used for the following functions. We are given to name 2 gears which are needed for the following functions. Okay, the first part, for isolating. Which switch gear is needed for isolating? So we can use a disconnector. So this one, we can use a disconnector. All right. The other part, we can use a switch disconnect, which is just one and the same. All right. So you can just have a switch disconnector in this way. That is another part that you can just have. On 3.12, which one is best for control? All right, so that is what we are given. All right, so this is, so we say the first part we are having a switch disconnector. In this case, we just need two used for the following. All right, then the other one, so we can actually use these ones for both. All right, or let's check what we can do. So you can actually apply or just use these two as they are. That is the disconnector. Yes, it's actually fine. Then on the control part, this one, we also have two for this one. Okay, so it's 2 by 2, which means we can have these ones. Let's see. We can have the relays, the contactors, the timers, and also the day-night switches. These are the ones that you're going to apply or to use in this case. All right, so that was our part of the question. In this case, all right, I just hope we saw everything. We've got 4 in this case. So out of 4, we can just pick any 2 in this case. All right, so let's check the other part. We are now given on 3.3 to name the protective device used to protect against the harmful effects of the following faults. So what is the protective device that we can use? All right, so if you check this question also with the November 2020, they asked also this similar question. So this one, they do actually a repetition. Okay, so for phase imbalance, we can use phase balance protective relays. So here we can just use our phase balance. All right, that's so. So this is going to be protective or protection relays. All right, protection relays. All right, on high voltage surges, we can have lightning arresters. All right, so we can have our lightning arresters. All right, also here for short circuits, we can use fuses in this case for short circuits. To protect short circuits, we can use fuses, and also breakers. The breakers, these are the most important one. The very, very most important are the circuit breakers. All right, so you can use circuit breakers. All right, 3.3, explain the operation of a relay. That is 3 marks. The operation of a relay. So that is 3 marks for that. Okay, so in this case, we have got the operation of relay given as when the relay coil is magnetized, it attracts an ion armature. This movement closes and opens contact. So that movement alone, it can allow the closing and opening of the contact. So that is how a relay operates. All right. The other part of the question on question 4 is now on batteries. So you're given on batteries to first part is to state 3 advantages of lead acid batteries. Okay, we talked about disadvantages from the question of November 2020, if I still remember. So this part, they need just advantages in this case. Okay, so this is what I have, guys, for you. You can pick any 3 from these ones. We can say that they are relatively cheap, they are reliable, they are robust, we have got low internal resistance, deliver high currents, available in various sizes, and also easily available. So any 3 from these ones can be best for our description in this case. All right, so that is what we are given in this case. On question 4.2, briefly explain how a gel battery is charged during fast mode. How can we charge a gel battery? That is 3 marks for that. During what? Take note, during a fast mode. That is the most important part in this case. All right, so we are given that at the start of charging, in the fast mode, the full current of the charger flows into the battery as the voltage builds up a preset value. Once the voltage reaches this desired value, the battery is fully charged and the current begins tapering down. So this is how it operates when we are dealing at full charge. Okay, so this is when it is fully charged, the current begins tapering down. That is what is important in this case. So whenever we are dealing with a fast charge in this case, or a fast mode, or we can just say fast charging or fast mode, this is the description that you're supposed to be indicating in this case. All right. The last part of question 5 was on question 4 was to list 4 aspects to consider containing the care and the maintenance of lithium-ion batteries. So what are the aspects that you need in the maintenance? Take note, this is on maintenance of lithium-ion batteries. All right, so here I've got some of the points that you can use. Just pick any 4 from these ones. Okay, the first one, do not leave batteries unused for long periods of time. Okay, always check the batteries charge status regularly. Always follow the instructions of the manufacturer. Remember, the manufacturer's instruction is always given, and follow that instruction with regard to charging. Carefully monitor batteries which are recharging at the end of their lifespan. Then remove the batteries from devices and then store. Charge or discharge a battery to a plus or minus 50% of capacity before storage. Okay, then the other part, do not disable, disassemble or crash or to punch the batteries. You do not crash any part or to punch the batteries and so forth. So this is not supposed to be done. And also the last part that we have is do not dispose batteries in fire or water. So do not dispose batteries in fire or water that can affect. So in this case, we are to pick any 4. We are given list 4 aspects. So any 4 from this part. All right, so that was our question 4 on batteries. Let's check that a part of the question, which is question number 5. Given we are given in this case, this is on DC machines, where we are given state the function of the following DC machines in terms of energy conversion. In terms of energy conversion, the first part is a DC generator. In terms of energy conversion, this is the most important part. Read and understand the instruction. All right, so in terms of energy conversion, if we are dealing with a DC generator, it is used to convert mechanical energy into electrical. So you're talking about conversion from mechanical to electrical. All right, which is opposite now to the DC motor, which is on 5.12. We are now given for a DC motor, what is the conversion that is going to happen? That is now we are going to be to convert electrical input that is now being converted into mechanical energy. So that is what we have on a motor now. It's now converting electrical to mechanical. So that was the question. The other part on 5.2, we are asked to briefly explain the concept of back EMF as applicable to DC machines. 2 marks. The concept of back EMF. So if we are dealing with DC machines, what is it about the back EMF? All right, so the back EMF is simply the EMF induced in the rotating armature conductors of a DC motor, which opposes the applied voltage. So that is the induced EMF. It opposes the applied voltage in this case. All right, so that was our question 5.2. On 5.3, we are given to state the function of a first plate starter. 2 marks again for that. Okay, so a first plate starter can be given in this format as it is to limit the high starting current on a DC motor. Remember, DC motors, when you are starting them, they've got high current. So the first plate starter now is using to reduce that or to limit these high starting currents of a DC motor by introducing additional resistance to the armature circuit for starting purposes only. So that is why we are saying a first start. It's only for starting a first plate start. It's only for starting purposes. So you must be careful on that one. All right. So that is what we had on this part. If you had to check, that was 10 marks on this part of the question on DC machines. On AC machines also, we are given to list applications of universal motors. What are the applications? Where do we use, or the concept, where exactly are we going to have these universal motors? In this case, we are given the application. That is, let me give back this part so that you can see. I can't see this part of the screen, so let me just show back. So the reason is because of this 5.2 that I skipped here, 5.4 here, this one that I skipped. So on this 5.4, you're asked to draw a circuit diagram showing how the armature and field coils of long shunt compound motor are connected to the supply. So this was the part that I actually skipped. So this is the diagram that we are going to have. Let me show this part of the screen. All right, so this is what we have on our drawing. So what is important, what they are actually testing you in this case, they are testing you on this part, the shunt field winding connection, okay? The issue of the shunt field connection, the series field winding connection, this series one, the shunt, the series, and the armature connection, the connection itself, and also the supply. So this is what they test you: the supply, the armature, the series winding connection, and this shunt connection. So you're supposed to show properly your connections to obtain full marks for this one. All right. So now we can move back to our question 6.1, where we are given to list two applications of universal motors in this case. All right, so I'm just going to show you what we have in this case. In this case, we have got 4. Just check N6, so you can pick any 2 of your choice. We've got portable drilling machines. These are some of the applications: angle grinders, vacuum cleaners, sewing machines, food mixers, and blenders. So these are the applications that we can give for universal motors in this case. All right, move on to the other part of the question, which is 6.2, where we are given to explain how the direction of rotation of a single phase split phase motor can be reversed. Take note: a single phase split phase. So that is what we are supposed to be careful of. So in this case, our direction can be changed by this. The direction of a single phase split phase motor is reversed by simply changing the polarity. This question is actually same. They repeated also in the November 2020. You have to check that one. So it's all about reversing simply by changing the polarity across the main or the auxiliary winding, but not both at the same time. So you change either the main or the auxiliary winding, but not at the same time. You are supposed to be careful that you are not having this at the same time, but it can be changed in that way. You can have change of direction. All right. So that is what we have on 6.3. Draw a neat, fully labeled circuit diagram of a capacitor start capacitor run single phase motor. So it's a capacitor start, capacitor run single phase. All right. So this is what I have in this case. I'm going to show you the diagram that is applicable in your answering. Okay. So on your mark allocation, what is important, that what they need is to correctness of the rotor. So we've got our rotor in this case. Then the connection of the running winding and the auxiliary winding. Okay, so we've got our running winding here and our auxiliary winding, and the starting capacitor connected parallel with the running switch. Okay, so the starting capacitor with the running capacitor in parallel, then the supply. Okay, so this is the major part that you are supposed to show with the line, the live and what in the neutral from our supply. So with this, we can obtain full marks. Okay, so that was our question 6.3, ending our question 6 with 8 marks. On question 7, this is now on transformers. Okay, so we check this one on transformers. So in this case, we've got a single phase. Take note, what you need is to check, is it a 3-phase or a single phase? Because how you answer for a single phase, how you answer for a 3-phase is different. Okay, so luckily in this case, it's a single phase, which means we do not have much in this case. So we have got, we can just list our information. Is a supply of 220 volts, which means we are having our V1, which is the supply of 220 volts. The 10th ratio, remember 10th ratio is taken from any1 over any2 in this case, which is 1/8. It's given as any1 as to any2, that is primary as to secondary, which is 1:8. So it's 1/8, n1 over n2, or you can use np for primary and ns for secondary in this case. But in your formula sheet, they use n1 and n, so that's why I'm using the 1 and the 2. The secondary current is 2 amps, and the secondary coil has got 210. So we've got the current in the secondary, which is our I2 in this case of 2 amps. And we are given also the number of turns in the secondary, which is 200 turns in the secondary. So the question is to calculate the primary current, which is 2 marks in this case. Calculate the primary current, 2 marks for that. So how can we determine the primary current? We can take advantage of this part, all right, of our turns ratio in this case, all right. So this is 7.11. So taking advantage of the turns ratio, since we know that the turns ratio, that is N1 over N2, is also equal to V1 over V2, which is equal to I2 over I1. All right, so in this case, we are referring to this part and the current, so we can equate these two. So N1 over N2 is equal to I2 over I1, where we can substitute in this case our N1, that is N1 over N2. This is our turns ratio, 1/8. So 1/8 is equal to I2, which is the current in the secondary. We are given the current in the secondary, which is 2 amps. We need the current in the primary, which is I1. So we can calculate I1 by cross multiplying. We can calculate this value. That's 1 times I1, which is I1 is equal to 8 times 2. So that's 8 times 2, which is 16 amps. So this is our current measured in amps. So as we know, if we've got a single phase, the current as it is does not affect, so we just have to calculate our values direct as they are. All right, the secondary voltage, which is V2 in this case, that's our secondary voltage on 7.12. So we need to calculate V2. So where can we have our V2, which is the secondary voltage? So we can also apply the same turns ratio. Since we are given V1, this time we are going to use these two here, because we are talking about voltage. So we're going to use N1 from this one. We are going to use N1 over N2, our turns ratio, equal to V1 over V2. So this is V1 over V2. So N1 over N2, that's your turns ratio. You have this one, 1/8. 1/8 is equal to V1, which is the primary voltage of 220. Then we are to calculate V2. So we can also calculate V2, cross multiply V2 times 1/8 multiplies 220. So V2 times 1, that's V2 in this case, which is going to be equal to 8 times 220. If you cross multiply, we are going to have 8 times 220, these two multiply. So that means our V2 is going to give us 1,760 volts. So that's what we have on our V2 in this case. All right, so move on. The transformer rating, okay, that's 7.13. What is the rating of the transformer? So when you are asked to find the transformer rating, we are finding this from where? What determines the rating of a transformer? That is the apparent power, which is S, where we know that S is equivalent to the voltage times the current. So from S, we can determine the rating of a transformer. So the rating of a transformer is taken from apparent power, voltage, amperes. All right, so that's 7.13. So which means we have to calculate the apparent power, which is the transformer rating. So that's volt times, that's a volt amperes, which is voltage times current. All right, which are the volt amperes. So that means our S is going to be the voltage either in the primary times the current in the primary, or we can use the voltage in the secondary times the current in the secondary. We are going to have the same answer. All right. So having V1 and I1, we can see that here we have our V1, we have the primary voltage of 220 times I1, the current in the primary, which is 16. So if we multiply this, we can have this value, which is 3,520 volt amperes. Okay, which is the same thing for the secondary. We are going to use the V2, which is 1,760 times I2, the current, which is 2. In this case, we are going to obtain the same answer, 3,520 volt amperes. So the rating of a transformer is volt amperes, kilovolt amperes. So we can change, we can have this as apparent power from our apparent power S. All right, so that is volt amperes. Statewide transformers are rated. Why transformers are rated in kilo kVA, which is the kilovolt amperes, the one that we have been talking about, not in kilowatts. Okay, so why is it that we have transformers in this? Okay, so the description is that the losses that occur in transformers are independent of the power factor, which means they do not have any consideration that has to do with the power factor. They are independent. They do not depend on power factor. Remember, power factor, that's where we have got cos theta, and the cos theta affects the power factor, affects the true power, since we are given VI cos of theta. So they are not part of they do not depend on the power factor. So that's why the rating is only on volt amperes, which is only volt and what? And current. So that is the idea that we are given there. All right, 7.3. Draw a neat labeled vector diagram. So take note, in this case, we are to have the vector diagram of a transformer working at no load, 3 marks. All right, I once had a sketch of this one, just showing you from calculations, but this time they need you to have a sketch or to draw this one. Okay, so this is what we have. We are going to have our no load current with our magnetizing component in this case, and here we have got the theta, which is the angle that is taken from our power factor. So take note, from your power factor, that is where we are going to have this angle. And that is our same part here, which is from what? From the magnetizing. Remember, it works with the flux. So this is going to be affected with flux. Okay, so the mark allocation is mostly on this component, the no load component and the magnetizing component, just one mark, and the issue of what? Properly indicating the angle. Remember, I also said this angle at this point is same as the angle at this point. So this can help us to calculate the magnetizing component or whatever that you're given according to your diagram, because these two, they are equal from the concept of what? From the concept of Z angles, alternate angles. All right. So that is what we had in this case. We check the other part of the question, okay, so that was the last part of question 7, having 10 marks. All right, let's check question 8. On question number 8, we are given to explain the following concept that is on earthing. All right. The first part, 8.11, that is leaking current. What do you understand by the term leaking current? So in this case, this is the leaking current can be expressed as the flow of electric current to earth as a result of deterioration of or damage to the insulation of cables, appliances, or other connected equipment, which is extremely hazardous. So this is, it is very, very dangerous. That is extremely hazardous. Okay. So that is what we are given in this case when it is to deal with leakage current. Then bonding to earth, 8.21, we are given bonding to earth. In this case, for bonding to earth, we are given as electrically connecting to earth all non-current carrying conductive parts of an electrical installation. All right, so this is what we are given in this case, what we have. And all right, state on 8.2, the function of an earthing chain. Okay, what are the functions of earthing chains in this case? Okay, so let me see what I have for you here, guys. So the functions of earthing chains can be, it is to provide a path to ground from all parts of an electrical installation for any harmful energy such as leakage current, static charges, and lightning discharges. So this is what we can apply on the earthing chain as the functions. All right, so we've got 2 marks for that. And sorry, that's 2 marks for that. And we move on to 8.3, indicate whether the following statements are true, false, by writing only true or false next to the question number. All right, the first part we are given, wire armoring in ground cables offer protection against mechanical damage. The wire armoring, okay, wire armoring, this is true. It actually offers protection against mechanical damage. Wire armoring and lead sheathed cables, you have a separate core that can serve as the earth continuity conductor. Do we have such? We do not have such. This is false. During the process of joining lead sheathed cable, it is easy to repair and restore the sheath cable. This is difficult for us to do, so it's false. The function of the sheath is to keep electromagnetic radiation in while keeping water and moisture out. Yes, this is actually true. All right, so this is true. All right, so that's why that one was just our theory, guys, just to test you. Do you understand deeper your cables? In this case, if you're dealing, do you understand deep? That is what they were trying to ask in this platform or on this part of the question, which is not that much. All right. Then question 9 is measuring instruments. In this case, we have a moving coil. So you check, guys, is it the information is going to tell you, are you going to have a multiplier on your circuit or a shunt resistor on your circuit? So in this case, we are given that a moving coil instrument with an internal resistance of 120 gives a full-scale deflection current of 0.04 amps through it. Determine the value of the additional component required to enable the instrument to be used as a voltmeter reading from 0, which is a voltmeter. That's as an we are going to use a multiplier. If we are to measure current, we use a shunt, okay, a shunt resistor. So in this case, we are going to connect it as a multiplier. So take note, we have the meter in this case, which is where we are given the series resistor, which is the one that affects the multiplier. So the multiplier is your series resistor, or RM. That is let me use this as series so that we do not confuse with the M that I'm going to use for this one, for the meter. All right, so we have the meter in this case. All right, so we have our meter in this case here. So we can just have our meter in this case. So like I said, I do not want to confuse you between the series resistor or the multiplier resistor and the resistor for the meter. So this is the internal resistance of the meter that we are given. So we want to measure voltages from 0 up to, which means across these points here, across these points. This is where we are going to measure our voltage. It is given from 0 to 50. that is the maximum voltage to use to supply is going to be 50. So here, this is the idea that we are measuring here from 0 to 50. So it means it's in series if you're dealing with voltage. If you are given the total current, maybe your total current is 2 amps, which means you are going to work with what? With a shunt, where this is going to be subdivided from the meter that we are given to the shunt. But in this case, it's to measure voltage, so it is supposed to be like this, okay, in series with a series resistor. With the series resistor, this being the meter, this one, the meter is where we are having these values like the internal resistance of 120 and this current of 0.04. So you've got an internal resistance across the meter of 120 ohms, and the current that is flowing through the circuit in this case is 0.04. So the 0.04 is the same as the current that is going to flow, because it's in series, so you're going to have same current throughout. So this is the current which is representing the series, also being part of our current that is across the meter. So it's part of the series resistor, and is also the current that is affecting our meter. So it's the same current. So the question is asking you to calculate this resistor. So how can we do this? Remember that in series, for you to accommodate this voltage, we can add the sum of the voltages that we are given in this case in series. Remember in series that the sum, this voltage of 50 volts is equal to the sum of the voltage, that is the current of the meter times the resistor of the meter in this case, plus the current of the meter, which is the same as the current across the resistor, which is affecting the series resistor. So these two, they are the same. So which means we can factor out if you want, then we divide, or since we are to calculate RS, we can transpose. So this is going to be 50 minus, okay, let me write as a proper formula so that in case of any values, if they change. So this V, the 50 that we have is the supply voltage, which is the total voltage in this case. So V minus, in this case, since we want to calculate RS, so we can transpose this part here to the left-hand side. So it is going to be a negative. So it's minus IM RM for the meter is equal to IM RS. Remember, we said IM and RS are equal, so that's why I'm just using IM, so that we can divide by IM both sides like this. We have RS in series, so which means our RS is going to be equal to V, which is our supply, minus IM times RM over IM in this case. You can even divide by IM each and every time, or you can just substitute here, guys. We can just substitute, or this formula, it can be given like this. Okay, let me just write. You can write your formula right like this, or you can divide this as any part is going to be fine. RS, which is our series resistor, if you divide by IM, this is going to be V over IM minus, this one is going to be IM RM like this, which is divided by IM. So this will cancel, you remain with RM. So it's going to be minus RM. So this is the formula that we can be given sometimes in our formulas. So if we are given this formula, then we can take advantage of that. We can just substitute our values. But if not, we can use this formula, or we can just on this formula here, we can substitute and make RS the subject. There's no need for even making RS the subject. Yes, we can just do that, or we can just make, and so this formula can give us RS. From this one, we can calculate RS. From this one, we can calculate RS. Okay, so I'm just going to use this one. That is V, my supply, which is total voltage 50 minus IM 0.04. So it's 0.04 times RM, which is the meter. The meter is 120 over IM, which is 0.04. So this is going to give us RS, which is going to be 1,130. So it's 1,130 ohms. All right, so that is what we had in this case. So like I said, we can even work it from this side. We can just substitute from this formula. RS is equal to V over IM, which is our total of 50 over IM, that's 0.04. minus Rm, which is the resistor across the what? Across the meter, which is 120. So that is 120. So we can even apply this concept. We still obtain same answer, 1,130 ohms. Okay, so that was the idea of the question in this case. All right. 9.2, you are now given to list 3 advantages of digital multimeter. What are the advantages of a digital multimeter? So we've got so many, but just pick 3 from these ones. We are given they are more accurate than analog multimeters. They reduce reading and interpolation errors because the value you are given direct, so it reduces those reading errors. All right, so we've got parallax errors are eliminated. No zero adjustment is necessary. They are available in smaller sizes. They are very robust, very strong. They also can be used to test continuity capacitors, diodes, and some can measure frequency. So multimeters, they can even be extended to measure frequency, which is well advanced in our technology life today. All right, so that is what we had in this part on this part of the question 9.2 to mark the last question on question number 9, having 6 marks on measuring instruments. The other part on question number 10, which is the last part of the question paper, is electrical reticulation and renewable energy. So in this part, they combined these two. Sometimes they do separate, okay, where electrical reticulation aside, renewable energy aside, but in this case, it was a combination of the two. So on 10.1, we are given to name 4 different types of power stations found in South Africa. Okay, so in South Africa, what are the different types of power stations that we have in this case? All right, so we have got a list of just 4 that is needed. So from this list, you're going to pick 4. So we've got coal-fired power stations. We also have nuclear power stations, gas turbine power stations, solar power stations, hydroelectric power stations, pump storage power stations, and the wind turbine power stations. All these are currently, we do not know currently, but they are in South Africa. So with any 4, you can pick any 4 from these ones, so that that was the requirement of the question. All right, the other part of the question, 10.2, is to list 2 advantages and disadvantages of radial feeder system. So take note advantages and the disadvantages of a radial feeder in this case. All right, so the advantages that we have is that it is actually the simplest method of energy distribution. The initial costs are low. The minimum cabling is required. Less maintenance is required. But we also have some disadvantages which do affect. So any 2 from this part, we can pick any. That is, a fault to result in loss of supply to the number of consumers. Regions closest to the transformer get heavily loaded. Consumers furthest away experience serious voltage drops that lead to fluctuations in the supply voltage. So this can be a very, 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 very big disadvantage in this radial feeder system. So meaning to say, having disadvantages and advantages at the same time. So that was required. With the aid of a neat labeled layout diagram, illustrate how a prime mover can be operated by a source of renewable energy. In this case, that is 4 marks, 10.3. All right, so let's check what we have as a issue of a diagram. So this is what I'm having from the distribution from the reservoir bank, which is our dam. We are going to have the water flow. This is the gate, the pressure tunnel to the sage tanks, the penstock, onto the inlet valve. Then from this part, that is where we are having our electric cable from the power lines to the transformer. Whilst L, this part, this is our draft tube, the turbine, the water flow nodes, and the electric generator. So these are the major points or the major part that you're supposed to be showing for you to obtain full marks in this case. Take note, this is 4 marks, so just half of each. So you're supposed to mention each part properly drawn. So that is how we can illustrate, or how we can present our prime mover in terms of its operation to bring out about the renewable energy. All right, so marking the last part of our question, that is question 10. So guys, as we prepare for our exams, this is what is needed. Question papers, work with more question papers, work with more revisions from past exam papers can actually help you prepare effectively for your exam, because most of the questions now, they just do repeat from the previous exam papers. So please do revise as much question papers as you can before exams. For now, that's it, guys, from Mezon African Motives on electrical trade theory N2. Till we meet again.